Let's continue with our discussion of when the Riemann Stieltjes integrals are actually going to exist. So we're going to introduce some kind of new notation and maybe some concepts that will make our discussions of the existence of these integrals a little easier to get a handle on. And these similar kinds of discussions are also used later on if you ever do a discussion of Lebesgue integration, that you'll see these same kind of concepts again. And so let's start off with a definition. So suppose that we've got a partition P of AB. Then for each one of those subintervals x sub k minus 1 to x sub k, we're going to take the supremum of all of the function values over those subintervals, and that supremum we're going to call capital M sub k of f. And kind of likewise, we can take the infimum of all possible values, of all possible function values over that same subinterval, and we'll call that little m sub k of f. Then we can define two sums. We can define the upper Stieltjes sum, which is just going to be the sum of the capital M sub k of f times the delta alpha sub k's, and the lower Stieltjes sum. So the lower Stieltjes sum is just the sum of the little m sub k of f times delta alpha sub k, and that's summed over all of our subintervals. Now, to kind of make our discussion a little easier, and we'll kind of see later on, and it'll come up that this is really not too much of a hindrance at all for what we're discussing. But let's make the assumption that alpha is going to be an increasing function on the closed interval AB, so that our delta alpha sub k's are all going to be greater than or equal to 0. Now, what that gives us, we know that the infimums are going to be less than or equal to the supremums on each one of those subintervals, and all of our function values are going to be sandwiched in between the infimums and the supremums on each subinterval. And since our delta alpha sub k's are all positive, it means that our lower Stieltjes sum is going to be a lower bound for all of our Riemann Stieltjes sums with respect to that particular partition, and the upper Stieltjes sum is going to be an upper bound for all of our Riemann Stieltjes sums. And so we've got this inequality for the lower bounds, the upper bounds, kind of bounding all of our Riemann Stieltjes sums with respect to this particular partition. And so kind of a natural question to then is, what happens when we start taking refinements of those partitions? What happens in those cases? Well, that's actually the content of our theorem 7.15 from our reference. So again, assuming that alpha is going to be an increasing function, if we've got a partition P prime that's going to be finer than a partition P, then the upper Stieltjes sum with respect to the refinement is going to be smaller than the upper Stieltjes sum with respect to P. The lower Stieltjes sum with respect to P is going to be smaller than the lower Stieltjes sum with respect to P prime. So we kind of get a narrowing by taking a refinement. We are narrowing what our upper bound is, we're raising what our lower bound is, and so we kind of get this compression going on as we continue to take refinements. Then also for any two partitions, P1 and P2, the lower Stieltjes sum with respect to P1 is going to be less than or equal to the upper Stieltjes sum with respect to P2. So there we're not really worrying about whether one partition is finer than another. Those inequalities are still going to hold. So let's see why that might actually be true. So since we're talking about just refinements, let's just say that we've got a partition P, and then we're going to add another point C that's not in P. So then what happens? Well, by math induction, because we're only adding a finite number of points, if we can show that it works for one point, math induction shows that it's going to work for any finite number of points. So let's say that our x sub n or x sub k is going to be our c value. So we've got our partition p prime, x0 for a, x1 all the way up to x sub k minus 1, then c, then x sub k plus 1, all the way up to x sub n. If we write out the upper Stieltjes sum for p prime, then that's just going to be our sum over our capital M sub i's. Then we can break that sum up into the terms that go up to k minus 1. Then our kth term, we'll separate that one out. Our k plus first term, we'll separate that one out. And then all the terms from k plus 2 on up to n. Now, we know that our m sub k of f is going to be, this is a primum over our kth subinterval sub x sub k minus 1 up to c. Capital M sub k plus 1 is going to be our supremum over our subinterval c up to x sub k plus 1. And so if we kind of draw a picture and compare those supremums, because we've got x sub k minus 1 up to c as being a subinterval of x sub k minus 1 to x sub k plus 1, then our supremum over the subinterval x sub k minus 1 up to c is going to be less than or equal to the supremum over the larger subinterval x sub k minus 1 all the way up to x sub k plus 1. And kind of think, okay, we've got a little more room there, our function could increase even bigger, and so it's only natural that our upper bound is going to grow as we have more room for our function to grow. And likewise, our supremum over c to x sub k plus 1 is going to be smaller, less than or equal to the supremum over the entire subinterval, and we'll call that supremum over our subinterval x sub k minus 1 to x sub k plus 1 m hat sub k. So that what this means when we go back and kind of look at our sum, well, we've got the sum over all of our terms up to k minus 1. And then our two terms that we separated out, the remaining terms above that, well, this is going to be smaller than our supremum over both of those, over the larger subinterval, x sub k minus 1, x to x sub k plus 1. So we can replace our m sub k plus 1 with our m hat sub k's, which we can just factor that out. And we are left summing our delta alpha sub k and delta alpha sub k plus 1. But remember that whenever we're adding those together, what form do they take? Well, alpha sub k plus 1 minus alpha sub c plus alpha sub c minus alpha sub k minus 1. Well, your alpha sub c's cancel out, and so we end up with delta alpha hat sub k just being the difference between alpha of x alpha at x sub k plus 1 and x sub k minus 1. So that when we take that and replace that back into our sum, we see that our upper Stieltjes sum, we can combine, our alpha sub c's cancel out, and we actually end up with the upper Stieltjes sum with respect to our partition P. And so the proof that the lower sum is going to get larger is going to be exactly the same. Again, really just using what does it really hinge on? It hinges on the fact that when we take our infimum over a larger subinterval or over a larger set, that our infimum is going to be less than or equal to the infimum over the smaller set. And that's kind of where what the entire proof is hinging on, again, in the second case. For the second part of that theorem, if we assume that we just got two partitions, P1 and P2, then we really just use the result we just obtained, that the lower Stieltjes sum of p sub 1 of f of alpha is going to be less than or equal to L of p1 union p2. So we take a refinement where we just dump the two partitions together. Then that's going to be less than or equal to the upper Stieltjes sum for the refinement, and that's going to be smaller than the upper Stieltjes sum for our partition p sub 2. So that one is pretty much just a corollary or just an application of the part 1 that we just did. All right, so now let's move on to another definition. And for this definition, again, we're going to assume that alpha is going to be an increasing function on our closed interval AB. And we're going to define the upper Riemann Stieltjes integral with f with respect to alpha as just the infimum of all of the upper Stieltjes sums for every partition P of our closed interval AB. So it's going to be the then for the lower Riemann Stieltjes integral, that's going to be the supremum over all of the lower Stieltjes sums for with respect to all the possible partitions P of our closed interval AB. And so kind of a little bit of a new notation here. The script P closed interval AB actually means the set of all partitions of AB. And so if we kind of go back and look at those definitions, that we're taking all of the upper Stieltjes sums are giving us the upper bounds. They're going to be upper bounds on all of our possible Riemann Stieltjes sums. So we are taking the infimum, so the greatest lower bound, the greatest lower bound of all of the possible upper bounds that we can have. That's our upper Riemann Stieltjes integral. And likewise, for the lower Riemann Stieltjes integral, we're looking at all of the set of all possible lower bounds that we can have on our Riemann Stieltjes sums. And for all of those possible lower bounds, we're going to take the least upper bound of all of those. And so kind of what we can visualize here is that the upper bounds are giving us the upper Stieltjes sums are giving us all of the set of points that are kind of above here, and we want to get the smallest of those values that we can possibly get. And then for the lower Stieltjes integral, we want to get all of the lower bounds, and we want to see, well, what's the biggest value that we're getting from there. And so what you kind of have in mind is this kind of squeezing effect for when our Riemann Stieltjes integral is actually going to exist. That we've got the upper bounds pushing down, you've got the lower bounds pushing up. As we refine our partitions, things are getting smaller, kind of squeezing together. And when those things squeeze together, then we're actually going to get the existence of our Riemann Stieltjes integral kind of all on its own. And that's kind of the intuition for where these definitions are going to take us. And so to kind of make sure that our intuition is doing what our definitions are actually following our intuition, it's probably a better way to say that. Let's see if we can prove some theorems about some of these new things. And so theorem 7.17 is, again, we're assuming that alpha is going to be an increasing function. And so first of all, that our lower Riemann Stieltjes integral is always going to be less than or equal to our upper Riemann Stieltjes integral. And so for that, let's just assume that epsilon is going to be greater than 0. Then that tells us that there's going to be a partition P1 such that for the lower Riemann Stieltjes integral, so we're taking the greatest lower bound, so we're taking the supremum over all of these lower sums. And so that means if we subtract a little bit from this upper bound. So we take our lower Riemann Stieltjes integral of f d alpha, we subtract a little bit from it, say epsilon over 2, then it's no longer going to be an upper bound, so this partition P1, the lower Stieltjes sum is going to be greater than our lower Riemann Stieltjes integral minus this epsilon over 2. Now, that same kind of thing being true, that because our upper Riemann Stieltjes integral was defined as the infimum, so it's the greatest lower bound, if we add a little bit to it, then we're not a lower bound anymore. And so there's a partition P2 such that one of these upper sums is going to be less than our integral plus our epsilon over 2. So really then, just going back and applying one of our consequences from theorem 7.15, we really have our lower Riemann Stieltjes integral minus epsilon over 2 is going to be less than our lower sum, our lower Stieltjes sum, but that's going to be less than or equal to our upper Stieltjes sum over the other partition, P2, and that one's going to be less than our upper Stieltjes sum plus our epsilon over 2. And so if we kind of rearrange things there, move the epsilon over 2 over to the other side, then we obtain this inequality where our lower Riemann Stieltjes integral is going to be less than our upper Riemann Stieltjes integral plus this epsilon. Now, epsilon being totally arbitrary, since this inequality is going to hold for any possible epsilon greater than 0, we can just drop it and our inequality becomes, our strict inequality becomes non-strict, and so we obtain our result that our lower Riemann Stieltjes integral is always going to be less than or equal to our upper Riemann Stieltjes integral. So kind of is that, aren't they always going to be equal, kind of is one natural question that we can have. And no, that's not necessarily true, and probably we don't have to look too far before we can think of one of these particular monsters for which the lower Stieltjes integral is not going to be equal to the upper Riemann Stieltjes integral. And for that, what kind of function is going to do that job? Well, our old friend that happens to be 1 at every rational number and 0 at every irrational number. And for that, we can just kind of make it the usual Riemann integration, just take alpha of x equal to x. So it's nice and continuous, and we don't have any problems throughout our interval 0, 1. Then, because the rationals are going to be dense, our supremum over any partition, doesn't matter what partition it is, the supremum over each subinterval is going to be 1. The irrationals are dense, so the infimum over any subinterval is going to be 0, regardless of the partition. That doesn't really matter. So all of our upper Stieltjes sums are going to be 1. All of our lower Stieltjes sums are going to be 0. And so in essence, what are we doing? We're taking the infimum over a set of singleton 1, which is just 1. We're taking the supremum over a set of singleton 0, so that one's just going to be 0. Our lower Riemann Stieltjes integral is going to be 0. Our upper Riemann Stieltjes integral is going to be 1. And so sure enough, in that particular case, they're not going to be equal. And so before we actually see that this does follow what our intuition says that it should, we have one more definition, and this is something called Riemann's condition. So we say that a function f satisfies Riemann's condition with respect to alpha on a closed interval ab if for every epsilon greater than 0 there exists a partition p sub epsilon of ab such that if p is going to be any other partition that's going to be finer than p sub epsilon, then we have 0 is going to be less than or equal to the upper Stieltjes sum with respect to p minus the lower Stieltjes sum with respect to p, that difference is going to be less than epsilon. And so again, kind of the idea that we're trying to get across in this is that the upper and lower integrals tend to squeeze into existence the actual Riemann Stieltjes integral. So kind of our last theorem, at least in this particular video, is theorem 7.19, which says that if we assume, again, that alpha is going to be an increasing function on closed interval AB, then these three conditions are all equivalent. Namely, that f is going to be Riemann Stieltjes integrable with respect to alpha on closed interval AB, that f is going to satisfy Riemann's condition with respect to alpha on AB, and kind of the third case that's going to be equivalent is that the lower Stieltjes integral of f with respect d alpha is going to be equal to the upper Riemann Stieltjes integral with respect to of f with respect to d alpha. So let's take a look at the proof to see why this might be true. So we'll start out by proving that condition 1 implies condition 2. So let's assume that f is going to be Riemann Stieltjes integral with respect to alpha. And suppose that we've got epsilon greater than 0. Since it is Riemann Stieltjes integrable, there exists a partition p sub alpha, or p sub epsilon, of AB, such that if we take any other partition P that's going to be finer than P sub epsilon, that the absolute value of the difference between any Riemann Stieltjes sum with respect to P and our integral is going to be less than epsilon over 2. So if we let P be a partition that's going to be finer than P sub epsilon, then by our definition of supremums, we can find these T sub k's in our closed interval, x sub k minus 1 to x sub k, such that if we subtract off a little bit from these supremums, that they're not upper bounds anymore, so m sub k of f minus epsilon over alpha sub b minus alpha sub a is going to be less than f of t sub k, so they're not going to be upper bounds anymore. Now note in this that we needed the fact that alpha of b is not going to be equal to alpha of a. We assume that alpha was increasing, so if we really had alpha of a equal to alpha of b, then it means alpha is going to be constant throughout this thing, and so pretty much everything's going to be 0, and that's a really trivial case. So forget that trivial case, assume that alpha of b is not going to be equal to alpha of a. So if we then turn around and do our sum, so if we sum over all of these k's, multiply by a delta alpha sub k, take these sums, then if we distribute our delta alpha sub k's, we're going to get the upper Stieltjes sum with respect to our partition P minus epsilon over alpha sub b minus alpha of a times our sum of our delta alpha sub k's. But that's going to be equal to, remember that our delta alpha sub k's are just going to give us a telescoping sum, so that's just going to be alpha of b minus alpha of a. Those will cancel out. For our upper inequality, that's just our particular Riemann Stieltjes sum that we'll call S sub 1. And so we end up with an inequality that our upper Riemann Stieltjes sum with respect to P minus epsilon is going to be less than this upper sum S, or this particular Riemann Stieltjes sum S sub 1. Now, kind of doing the same thing, the flip side of that, we can find t sub k primes such that if we increase a little bit, that we're not a lower bound anymore. So our m sub k of f plus epsilon over alpha of b minus alpha of a, then that's going to be greater than these function values at these t sub k primes. And so what we do, same thing before, we then sum over all of these things. We obtain a second Riemann Stieltjes sum, S sub 2. So that's going to be less than our lower Riemann Stieltjes sum plus our epsilon. Okay. Now, since S sub 1 and S sub 2 are just Riemann Stieltjes sums, we have that S sub 1 minus our integral is going to be less than epsilon over 2, the absolute value. We know that the distance between S sub 2 and our Riemann Stieltjes integral is also going to be less than epsilon over 2. And so kind of putting those two things together, writing out those inequalities, combining things, we can see that S sub 2 minus S sub 1 is going to be bounded above and below by epsilon and minus epsilon. So if we then look at the upper Riemann Stieltjes sum minus our lower Riemann Stieltjes sum with respect to this partition P, then we're just doing the old add subtract trick. So we subtract S sub 2, add S sub 2, subtract S sub 1, add S sub 1, kind of regroup things. Our first grouping, our upper Riemann Stieltjes sum minus S sub 2, that one's going to be less than epsilon. S sub 2 minus S sub 1, we know that that's got to be less than our upper bound of epsilon. And our last grouping, S sub 1 minus our lower Stieltjes sum, is going to be also less than epsilon. So epsilon plus epsilon plus epsilon, this can be less than 3 epsilon. And so our difference can be made less than a constant times epsilon. If we scaled everything just right, we can get it smaller than epsilon. But that proves what we need it to prove. And so that takes care of the first case, the first implication. So the first condition being Riemann Stieltjes integrable, implying that we meet the Riemann's condition. So then for the second one, we want to go from, suppose that we're satisfying Riemann's condition, and we want to show that the upper and lower Riemann Stieltjes integrals are equal. So let's assume that Riemann's condition holds. Then we've got a partition P sub epsilon, such that for any finer partition that we have that our upper partition minus our upper sum with respect to the partition minus our lower sum with respect to the partition is going to be less than epsilon. So if we do a little rearranging, we can move that lower sum over to the other side. And what we have then is that our upper Riemann Stieltjes integral is going to be less than u of p of f of alpha. Okay, so that's really pretty much just by the definition of this is the greatest lower bound of all of these things. And similar things going to hold that our Riemann Stieltjes our lower Riemann Stieltjes integral is going to be greater than our lower sum, because that was the least upper bound. And so we just have this chain of inequalities that our upper Riemann Stieltjes integral is less than our upper sum, which is less than our lower sum plus the epsilon, which is less than or equal to our upper Riemann Stieltjes integral, or our lower Riemann Stieltjes integral rather, plus our epsilon. So that gives us this chain which holds. So our upper Riemann Stieltjes integral is less than our lower Riemann Stieltjes integral plus epsilon for any arbitrary old epsilon. And so that means it's going to hold in general for that our integral from a to b, our upper Riemann Stieltjes integral, was going to be less than or equal to our lower Riemann Stieltjes integral. The flip inequality already holds. So we know that the upper is already going to be greater than the lower, and so what that means is they have to be equal. So that this condition we just showed, along with our theorem 7.17, shows that our upper Riemann Stieltjes integral is equal to our lower Riemann Stieltjes integral. Okay, so that takes care of condition 2 implying condition 3. So now let's go see if we can complete the circle and see if we can show that 3 implies 1. So let's assume that our upper and lower Riemann Stieltjes integrals are equal. So that gives us a target. Let's call that target A. Then taking epsilon greater than 0, we've got a partition P1 such that if we take our greatest lower bound, add on, we're not a lower bound anymore, so there's a partition that's going to be smaller. Our upper sum with respect to this partition P1 is going to be smaller than that. Likewise, there's another partition P2 such that our lower Riemann Stieltjes sum, if we subtract off a little bit from that, then we are not an upper bound anymore, and so there's a partition that's going to be a lower Riemann's sum that's going to be smaller than that, or it's going to be larger than that value. And so then, kind of as a consequence of theorem 7.15, that our a plus epsilon is going to be greater than this upper sum with respect to P1, but that's going to be greater than or equal to this upper sum with respect to the refinement P1 union P2. And likewise, a minus epsilon is going to be less than our lower sum with respect to P2, but that's going to be less than or equal to our lower sum with respect to the refinement P1 union P2. And so if we have any old refinement P, any refinement P that's going to be finer than P1 union P2, then same inequalities are going to hold. A plus epsilon is going to be greater than the upper sum with respect to P. A minus epsilon is going to be less than the lower sum with respect to P. And so for any Riemann Stieltjes sum that's going to be kind of sandwiched in between our upper sum and our lower sum, that gives us that it's going to be sandwiched in between a minus epsilon and a plus epsilon, but this is equivalent to the distance between this sum and a being less than epsilon. And so that shows that f is going to be Riemann Stieltjes integrable with respect to alpha on our closed interval AB, therefore thereby completing our circle, and so showing that all of our conditions are equivalent. So hopefully this has allowed you to see some of the machinery that we're going to use later on kind of in the development, maybe proving some of our applications and being able to show that under what conditions our Riemann Stieltjes integral is going to exist. And for that, it's really just developing the tools to make our life a little bit easier, kind of based on our intuition of, well, we can squeeze things into existence from above, squeeze them into existence from below, which is kind of going back all the way to the beginning when we first saw Riemann integration, and we had our overestimates with our rectangles and our underestimates for our rectangles, and as we improved our refinements, we squeezed those things into existence. So this is just kind of a natural extension, so same tools, same ideas that we saw back previously. So hope you enjoyed this, and more videos to come.